Bueno, muy buenos días a todos. Principalmente saludándolos y agradeciéndoles su participación en este evento inaugural de la Semana Internacional. El International Week 2023 es un evento de internacionalización en casa que se realiza todos los años en la Universidad Pontificia Bolivariana, el cual es un evento que se realiza para procurar y propiciar el conocimiento del mundo en nuestra comunidad universitaria y de las regiones donde hacemos presencia, a través de actividades académicas, culturales, recreativas en torno a un país invitado. Para este año 2023, el país invitado, nuestro país de honor, es Países Bajos. Y es por ello que iniciamos nuestra International Week con una conferencia internacional titulada La industria de diseño de estructuras eólicas offshore. Nuestro invitado internacional es el señor Alberto Mario Striedinger Pinilla, ingeniero experto en estructuras eólicas offshore. El señor Alberto es ingeniero mecánico graduado de la Universidad del Norte, con maestría en energías renovables, con 7 años de experiencia en diseño estructural para turbinas eólicas costa afuera. Entonces, le damos paso al señor Alberto Mario para que inicie su presentación.
Buenas tardes. Buenas tardes, ¿me están escuchando todos? Bueno, yo supongo que me escuchan.
Sí, te escuchamos bien, Alberto.
Ok, listo, muchas gracias, muchas gracias. Muchas gracias a la universidad y a Rafael Turán en especial por haberme dado esta oportunidad de darles una presentación a ustedes. Entonces, sin más ni menos. Ok, listo. La siguiente presentación se la voy a hacer en inglés. Debido a que parte del objetivo de la internacionalización es también practicar este idioma que además de eso es bastante usado en este campo. Sin embargo, la mayoría de la información que ustedes van a ver presenciar aquí en esta presentación está tanto en español como en inglés. Ya después de pasado el tiempo, le pasaré este documento a la universidad para que ustedes lo puedan tener y verlo a futuro. Entonces, comencemos. So the table of contents, we are going to split this presentation into practically 9 topics, a bit of myself, a bit of the climate crisis overview, what is wind energy, so you know exactly what we are talking about within the industry, the key aspects such as the size, the project stages that one has to undergo, the structures and the substructures, a few examples of the offshore wind farm projects, and some useful apps in your phone that you can actually download now. They are free to start exploring a bit more about this industry. And later on, the fundamentals of the energy extraction, so only the fundamentals, a bit of the basics of the wind turbine design, focus on the primary still, and afterwards, some questions if the audience may to have any questions about this topic. And just before that, let me turn on my camera. Yes, that's better. I think you can see me now. Hello. All right, so first a bit about me. So I'm a mechanical engineer, graduated from the Universidad del Norte in Barranquilla from 2005, 2010. Later on, I did 1 year in the United States for my bachelor as well. I ended up doing a master in renewable energy technologies, among those wind energy, which is the field I specialized in and consecutively started working in the TU Eindhoven, that is in the Netherlands, with the University of TU Delft. Later on, I went on working as a structural design engineer and the lead design engineer since 2014 at a company called Siemens Gamesa, until recently 2021, when I finished my my job, my work in the company. I also have my leisure time, of course, like any of you have hobbies. Mine is a bit of performing arts and looking a bit behind the cameras. So the climate crisis overview. Why is this important? Just to name a few aspects of what the world is going through. You have, for example, in 2019, there was a catastrophe happening in Zimbabwe and Mozambique. You have the extreme fire events that happened in Australia. The 2019 was the record hottest year, especially in summer, obviously. And in 2020, you had the worst fires that the country could experience. We also have floodings in Bangladesh, Indonesia, and obviously we have natural disasters also happening within our country, in Colombia. These just are a few pictures of what is happening around the world, just a little bit, and hopefully motivators for you to care and go into renewable energy industry and how to solve the climate crisis or try to tackle it. The news becomes harder once you realize that according to the United Nations, these climate crisis, the continent that's going to be most effective is Latin America. So it's practically us. So that's something to keep in mind, because country policies should be aligned in order to mitigate the effects that this is going to have on everybody, especially in South America. Why is this happening? Well, this is happening due to the greenhouse gas effect. If you go to the United States, to the department, they have this department called NOAA for the atmospheric and oceanic sciences. We can see that the CO2 emissions have been increased rapidly. At the right hand, you have a plot which is from 2007 until 2019, or well, actually until now, which is a rapid increase. But if you compare it to the left, which is what has happened around 800 years before, we see a cycle going up and down. It's only now when the human activity is practically more prominent that we have an increase in these greenhouse gas emissions. Now, why is this important? What does it have to do with me, with us, with the climate? Well, one example of this is the melting of the Antarctic and the melting of Greenland ice sheets, right? It's so drastic that if you are going to approximate this is around 151 plus 275 billion metric tons per year. Just to try to glance it, if you take this value and you say, okay, from 2002 to 2020, think of an ice sheet of a depth of 1 meter. That will cover around this much of an area, 427,000 square kilometers, which in this time frame between 2002 and 22, it's around 7 times the size of Colombia, or practically the size of Brazil. So this is a way to use the data that you can find freely available and transform it into something practical. And this is just one aspect of the climate crisis, right? There are also health problems related to it. There's trash and plastic that people and the industries are dumping in the ocean. But by acting together, we can really repair this damage. And for example, focusing not so much in fossil fuel-based energies, but more in renewables like wind, solar, geothermal, and so on. And something very important, besides the engineering aspects and the technologies, is to actually change our behavior to come up with new strong policies. We need strong leaders, private companies, as well as governments to take action with the people. But what is wind energy, right? Now that we are interested to go into renewable energies to help to tackle the climate crisis, what on earth is wind energy, right? This is a picture in the background of an offshore wind farm, and the other one, it's also when someone doing just kite surfing. So it's not only just a place where you can put your turbines and start generating electricity. It also can be integrated with sports, with leisure activities, something that is very difficult to find with other energy sources. In the industry, we also implement or are designing for the present and for the future for the deep waters. And in this case, you have a floating structure, which is not fixed at the bottom for a wind turbine. This one here, for example, I have a video. It's not recently recorded, but it's practically the view you can actually have from, and you can see the size of the machines that we're talking about. Let's see if this reproduce. The video does not have any audio at the moment because I'm talking from the phone, but at least you can see that we're talking about these. This is called it's not a vertical axis wind turbine, it's a horizontal axis wind turbine. There's also new technologies coming up, perhaps not as massively implemented as the normal wind turbines, but one of those is the kites. The kites can go at a height which is way above the height that the current wind turbines and future wind turbines will be able to reach. What is wind energy? Everything is rotating because of the blades of the rotor nacelle assembly. So what you see to the right, this is just a snapshot of how you look at the rotor. And you can see a bit of a cross section, a bit the twisted blade. But what is it? If you take the kinetic energy in the wind and transform it into mechanical power, so therefore generate electricity and feed it to the grid. So that is what we discussed about what wind energy is. So you have an inflow and you have an outflow, which is represented in the small diagram that I just said there in the right corner. And the rotor, you can consider it as just a flat plane where the electricity is extracted from. So we're only going to talk about horizontal axis wind turbines, which have three blades, is the most implemented. And they are spinning due to the lift forces along the blades. And this is caused by the wind passing through it. The energy, as you remember from your fluid mechanics courses, and the kinetic energy in a fluid is proportional to its density and to the cube of the wind speed, the velocity in this case, right? But there is a maximum that you can achieve. If you take the energy balance into account, you have the energy flow going in and energy flow going out. You take a ratio, it's practically the coefficient of performance is a way of measuring the efficiency of a turbine, which is the output generated, the power, the PR divided by the energy incoming in the flow. And with that value, you can have an estimate of what your nominal power capacity would be. There is a maximum to what you can get. And that is, with this formulation, it's very basic. It considers a stream flow through the rotor. This was work done in 1915 to 1917, so more or less. So the maximum efficiency you can get, and therefore the one you're not going to achieve, is a 59.3% efficiency in conversion. Right? This does not take into account any losses. Does not take into account the rotor itself actually at this moment. So it's a top, it's a maximum. To give an example of what does this mean? If you take the same formulation, let's say you have a 10-meter wind speed, right? You have a 100-meter rotor diameter. It's quite big, around a radius of 60 meters. If you have a maximum power coefficient, let's say 0.593, is not what a turbine will have, obviously, but it's the maximum you can get. So with these dimensions at this wind speed, the maximum is 4.10 megawatts, which means any turbine about this size will never reach 4.10, but it's the maximum it aims to, right? That's the theoretical limit there. Now, the power curve. In practice, the power coefficient varies with the wind speed, and therefore the power that the turbine is producing also varies with the wind speed. And these are tailored. It's very difficult nowadays to find one for a turbine because these are tailored for the site and for the client. This is either for onshore, also inland, or either for offshore wind turbines. Both cases are applied in this manner. Now, the main components that I want to that we will discuss in this presentation are the RNA, which is short for the rotor, which is practically where you have the 3 blades, and the hub, which is the nose in the middle. The nacelle assembly, so rotor nacelle assembly, which is I'm not sure if you can see the pointer of the mouse, but you can see practically here in the top corner in yellow. The nacelle is where most of the electrical components, the gearbox, and other aspects are housed in together. You have the foundation, you have the tower to the right, which is installed offshore in a few sections, 2, 3, 4 sections. You have the foundations in the bottom, which could be a monopile, which is a big, very, very big cylinder. Or you could have also the jacket structure, which is a lattice structure. And the plant layout, it's very important to know about the plant layout, because the wind farm is not only the wind turbines. To consider that would be a bit naive, not so realistic. So what do you have? You have the wind turbines in the farm. You have the cabling that helps you to make a grid connection with, not a grid connection, first a connection within the turbines. These cables are then either going to a substation or directly to a high voltage converting station from AC to DC, because it needs to be transported to the land, right? And in this case, I set 2 pictures of 2 projects. One is a sea-made project, one of the largest offshore wind energy projects in Belgium. The other one is unmanned. I think it's in the UK. It's also an HVAC/DC station, it's a convert station. Then of course you have the connection going to the land, and in the land, hopefully you can see the picture you can see the relative size of the cable housing, because there are many cables going through that one compared to the worker, right? Those are the cables we're discussing about. And then obviously later on you have the transforming station. You go from DC to AC again, and then fed back to the grid. So that's what we mean by grid energy. So to summarize it about the horizontal axis wind turbines in the offshore. Because the performance characteristics and the power curve and the power coefficient curves for market wind turbines are not readily available, right? You can still make use of reference wind turbines, especially for this presentation. One of such is from the National Renewable Energy Laboratory in the United States, in short for NREL. I want to show you the stages of the importance of these plots. The first one, this is a reference turbine of 15 megawatts with a rotor diameter of 248 meters. It's quite big, actually. It's gigantic. What is important for you to understand from this plot, right? One is the cut-in wind speed. The cut-in wind speed is the wind speed at which the turbine starts producing electricity. It's not the wind speed at which it starts rotating, because that's lower. It's the wind speed at which it starts producing electricity. Then it ramps up, so your power coefficient starts to change. It starts slightly getting better. You reach a point in which you are producing your nominal output, in this case 15 megawatts, right? That's the nominal power of this reference turbine. And at that point, you could try to go up, but the machine will not handle it, right? So you have to cut it. You have to tap the maximum power that you are performing. And to do that, the blades are pitched, so they are rotating on their own axis. So your power coefficient starts to decrease until you get your cutout wind speed. In this case, it's around, I think, 25 meters per second, exactly. That means after that, you're not producing any power, it's cut out. Now the blades are twisted across the blade section. To the right, hopefully you can see a bit of what it means. If the blades would not be twisted, you would definitely see right away a profile easy to identify, right? Why are they twisted along its axis? The reason is to ensure the optimal performance. Why? take a look at, I know it's a sketch, I cannot really properly show it a blade cross section at this moment, but what happens when the turbine just starts and is fixed, it's not rotating. Once the flow goes through it, you have a lift and a drag force caused by the pressure difference in the above and below the airfoil cross section, right? But once it starts to rotate, right, the relative wind speed, so the wind speed velocity relative to the blade starts changing. It's not horizontal anymore because it's rotating. So you need to incorporate as well the tangential velocity, which, if you remember by your courses of dynamics, it does change with respect to the radius where you are. So the rotational speed, the RPM, is not changing, right? At a fixed RPM, let's say, but the tangential speed is. And because the tangential wind speed is changing, so the angle at which the wind is going towards the blade, it's called the angle of attack, it's also changing. And therefore your lift is changing. So if you do not twist it and you do not change the profile along the blades, you're not going to ensure the optimal performance. So that's why these blades are twisted. Now, how do you know you're twisted? Hopefully you can see that from these pictures. I accumulated, this is like 4 pictures. To the right, these are all different turbines, by the way. Further to the right, in the installation of a wheel farm, you can see that the tip is not so wide, and increases its width, and then decreases once it reaches the center, right, the middle of the rotor hub. Also in the transportation, you can see how this goes, right? So just to have a visual idea that indeed the blade cross section is being twisted and the airfoils are also changing. That means the cross section area. Now, I want to tell you about some key aspects. A few things about the size of these machines. The ones that we have been, that the industry have been dealing with, and the current ones are the ones to come, actually like this year, next year. Also about the wind profile and the load types. That means the loads that these machines have to sustain in order to perform during their lifetime, which is roughly 20 to 25 years. The worldwide, not perspective, but the worldwide distribution of the energy, so to speak, so you know which countries, which continents are the leaders. The project stages for the investment, and starting from zero practically until decommissioning, and a little bit about the plant economics, the core basics only. Right. So in this one, this is a nice picture from Dong. It's the old name of one of the leaders, now called Ørsted. So this is a span of 25 years, starting from 1991 to 2016. We have gone from machines producing around 450 kilowatts to 8 megawatts. Now, in size, what does that mean? If you happen to see, I put a few pictures over there of the Boeing 737. So we have gone to, well, not me, I was not participating in 1991. I was very, very young. But we can see the diameter of a rotor spans from 35 meters up to 164 meters, around 160 meters plus, in a span of 20 years, right? So it's quite an increase in size. So these are the machines that nowadays are going to be installed around heights of more than 100 meters with diameters of more than 160 meters. But how big can this actually be? Yeah, the line of planes there is not a fault by the PowerPoint presentation. That this is around eight Boeings in a line, right? And that's exactly the new span diameter is around 236 meters of the new incoming offshore wind turbine that Siemens Gamesa is producing. It has a rating power of 14 megawatts, right? So if you take a look at the previous one, that was 8 megawatts. We're almost doubling the size of the capacity, right? And key players I'm not mentioning all of those, but you have Siemens Gamesa, Renewable Energy, so SGRE as a turbine manufacturer, constructor. You have General Electric as well, who is making a turbine called the Heliade X, if I pronounce it properly. You have Vestas and MHI Vestas producing this type of machines as well. And well, normal wind turbines, as mentioned before, you have around 160 meter diameter, 120, 140, and so on. But what about the mass? What about the mass of this structure, taking into account the tower and the rotor nacelle assembly? You can easily go, actually not from 400, but let's say 600, 700 until 1 ton. Why? Because the tower on its own, which is the steel structure below the turbine, below the rotor, can weigh as much as 400 and 600 tons of primary steel, which is only the wall thickness and the flanges and the bolts, etc. Mainly the shells, the whole structure, right? Take, for example, this is a project I was fortunate enough to work in when I was working with Siemens. It's called Yunlin. It's in Taiwan. It has 80 turbines of 8 megawatts each, with a diameter of 167. The weight of this structure, without considering the foundation, is around 800 to 900 metric tons, right? So we're not talking something you can lift very easily. Now, how does this compare, like now that we discuss about the capacities, with respect to thermal plants? I decided to take a look at the ones in Colombia. So these are by no means all of them, but what I could find. So I put the map to the right hand. This is the website where you can find it, from Concentra. So if I'm not mistaken, around 30% of the capacity, the energy capacity in Colombia, which is 18 gigawatts, should be for thermal power. We have Termo Barranquilla, Termo Cartagena, Termo La Guajira, 290 megawatts, 180 megawatts, and I think Termo Barranquilla, because it has 3 plants, right? So it's around 900-ish megawatts. This is gigantic, right? But wind energy is also reaching those values and more. Yunlin on its own has 640 megawatts. It's a gigantic wind farm. Another one, Westernmost Roof, located in England. It's an old one, well, and not extremely old, but not so recent. It's 210 megawatts. If you see, it's already almost the size of Termo Guajira. Not the same, but it's reaching there. It's bigger than Termo Cartagena in its nominal capacity. You have CIMAE, which is the largest offshore wind farm in Belgium, around 487 megawatts. It beats immediately Termo Cartagena and Termo Guajira. Now, one of the key aspects, how does the wind come to, like, we're using wind, right? So it's a little bit important to know about at least some basics of this. So I'm going to go a bit fast. So the Earth is heated up by the sun, right? Mostly in the equator areas, right? Because the orientation, how it is, and it's rotating on its axis, etc., etc. So the heat flows from the hot zones to the cold zones, and this is one of the main drivers for what we call the global air circulation. So these are I'm not going to say your prevailing winds, because that's a term in atmospheric sciences, but you could sort of think of that. And if you add the effect that the Earth is rotating on its own, then you have all the flow patterns you can imagine. In order not to go so complex, what we care about for the implementation and the energy extraction of the wind turbines is what we call the planetary boundary layer. So if you go back to your fluid mechanics course, if you remember a flow going on top of a plate, you have a non-slip condition just close to the plate, right? So the wind speed there is 0, and it slowly increases. Right? It starts to increase until it reaches a value that you could sort of consider almost constant, right? Something like this happens as well within the atmosphere. And that area where you have your boundary layer, your wind speed profile, is called the planetary boundary layer. It has a height of approximately between 1 and 2 kilometers. That's where the turbines are, That's the wind speed profile that you care. But how on earth do you get this? What point you need to have measurements. Now, the geostropic wind is this wind above, just above the planetary boundary layer, which, if I'm not mistaken, has a constant wind speed and it's just dominating over there. But between that wind speed and the soil or the sea, you have the wind speed profile. What is a wind speed profile? You have measurements that will tell you the wind fluctuations, that mean the turbulent part of the wind speed, and you have the mean, the average part of the wind speed. But you need these profiles. How do you get those profiles if you're on the offshore, right? It's not that you can just simply go there, right? But projects have been made in order to actually gather this data. This is a MedMast station. I think it's more than just a MedMast station. It's a weather station. It's called Finno number 2. Is actually between Germany, Sweden, and I think Denmark, somewhere over there. It's in the Baltic North. It's in the sea over there. And this one is implemented to have recordings of the wind speed along certain heights. And that's how you measure them. Then, of course, later on, these are plotted. And what you see in the middle is just a plot of the height in the vertical axis, and in the horizontal axis, you have the wind speed. These are the profiles that you need in order for the power extraction. I mean, to make an assessment. This is a link I'm providing you guys here, where you can find more information about this project. You can get the data. You can do all sort of stuff with it and learn more about it. One example. It's not exactly the same MedMast, but I want to make an emphasis of what is the difference between wind speeds in the land and wind speeds on sea. In this case, we have actual measurements from, well, it's a report, right, from the Energy Research Center of the Netherlands, which is ECN, and DNO. These are both institutions within the country of the Netherlands. To the right, you see geographical representation where all the offshore points were for the measurements of the wind speeds, right? And there's one little point there in the inland where you have your reference inland wind. To the left, we have a plot this from one of these reports stating the wind speed in the light blue, the wind speed profile, up to a height of 600 meters, so more than half a kilometer, of how the wind speed profile is on land. And all the other colorful ones, we don't need to go which one is what, but these are all in the offshore, right? Immediately you can see at 10 meters per second, which is the first value you see in the vertical axis, you have wind speed of 4 meters per second at land, and you have wind speed of 8 point, I cannot really see too much, between 8 and 9 meters per second in the offshore. Give me a second. Right? And it increases and it reaches a constant value at around 250, 300 meters height. What does this mean in practical sense? Well, let's take the case for a hub height, or a height of you're going to extract energy at 100 meters with a 120 meter rotor and a 220 meter rotor. If you have an average power coefficient of 0.45, which, by the way, is not so far-fetched. Most wind turbines should have a power coefficient, a maximum power coefficient around this. That means that at this height, you can pick and choose any of the wind profiles there you have there. But if you just take a random one, you can take one at 10 meters per second wind speed at this height, which should be probably one of the green yellow ones. But an inland, you have a wind speed of 7.2 meters per second. There's a difference of what, 28%? It's a lot, but let's see how much difference you get in power. Using the formula, the power coefficient, the density, the area, and the wind speed to the power of the cube power. The difference is dramatic. You go from, let's say, rotor of 120 meters with this idealized turbine, right? you go from a power of 1.16 megawatts to 3.11. So you almost triple this thing. And if you go from a rotor of 220 meters, and then from the inland to the offshore, you get 10 megawatts, almost 10.5 megawatts. So the increase is dramatic. It's more than 28%. That should tell you right away why investors are interested in building more offshore than onshore. It's not the only aspects that are taken into consideration for a decision like this. However, we can. Oh, my phone is done. Just because this is how I talk to you guys. By the way, is everything clear so far? Can you guys understand my English properly? What we've been discussing, the introduction. Okay, and then I will continue. Let me know. Okay, one of the key aspects, it's advantages because we already see we have more potential for energy. The wind speed is higher over there at the same height, right? The noise and vibrations, at least for public, because to use the wind turbines inland, you have noise and vibrations that are close to the population, etc. So people do complain about that. And installation in the ocean, even though it's more expensive, you can build bigger wind farms, bigger and wider wind farms than inland. You do not have to not destroy, but you don't have to use that much land to have this. Transportation of the structures. The transport it's also costly, but it's also very costly and very difficult also inland if you want to make such heavy wind turbines, heavy structures, right, that you cannot transport in roads. In the land use where all of them have environmental impact, offshore you have to make an environmental assessment for marine life as well. Right, and land use is obviously different inland. Now, the wind speed profile and the load types, especially I'm going to focus now on the offshore. There are three major sources that you will get your loads. Mainly the wind, as it interacts with the rotor and it gets transport. On all those loads get, so to speak. Give me a second. Okay, yes, I'm seeing a question about the floating structures, their capacities, and possible utilization implementation in Colombia, right? Okay, they're actually they are coming new. There's a project called well, it's not new already. High Scott Highwind and Highwind Tampen. These are located in the UK. Let's see if I can show right away. Yeah, I think I can show right away. They go very fast just to jump to that one. Yeah, it's not. Yeah, here. Okay, this is not the one I'm talking about. This is in France. This is called Provence Grand Large PGL. It is a floater design concept, and mostly you use this when the water depth is just too high. It's too deep. In this case, the water depths are 70 meters, right? So if you would produce a jacket or other kind of fixed foundation, the costs are just too expensive for the transportation, for the installation, for the production, and for the design itself. Now, the size of the turbine itself most likely is not going to be too much different than the fixed offshore wind turbine. What is changing, though, obviously, is the floater. So the floater can be, well, the idea is that it floats, right? So there is there's a ratio between its weight, and you see, for example, here some containers there that help to make this unit float. But this wind farm just to give an example, each turbine is 8.4 megawatts. It's not yet installed though. It's not yet installed. It's a French project that should regain its momentum in this year or next year for the final stages of for starting the construction installation. Not so sure about that one. It's 3 units, so it's a test. And the difficult aspects of this is that the dynamics are different. It's not fixed, so you for in this case you use tensile lines, or not cables, but you can call it chains, so to speak, to hold this thing together. Now, the applicability in Colombia, you will have to check first, actually, where to install the fixed offshore wind turbines. It's my opinion to first go to the fixed offshore wind turbines, unless you bring experts already that know this topic, and not by person, but the companies, right? Because there's a roadmap that the government just issued about offshore renewable energies and wind as well. So there are certainly possibilities to implement this in Colombia. But as a country, I think you first need to take some initial steps into it, not just only the floating aspects. They have challenges, by the way. They have quite some challenges. This is why, for example, this project only has 3 units. It's going to be sort of like a test. I think Hywind Tampen, Hywind Scotland in the UK has 6 turbines, right? So it's not like, let's say, for the next 2 or 3 years we're going to work on a project and install 20 floating turbines. I don't see that as a possibility nowadays. It's too early stage. That's my honest opinion, right? But if you want a wind farm of 40 units, 30 units, 80 units, then the companies will definitely go for onshore, and also we are dealing with different water depths, not 70 meters, for example, but 13, 20, 15. You can even go up to 50-meter water depths. I don't know if that answers your question. Maybe you guys can write it down in the chat box to see if that give you an answer to that. Yeah. Well, if so, then I continue. The type of loads that you will get. I will say a little bit about the floating here. Let's say for fixed ones to the left. So you have the wind loads in the rotor and the wind loads in the tower, right? You have the wave loads that are obviously higher at the mean sea level, right? You have your splashing zone, which is where the waves are breaking towards the structure or to the structure, and you have the current. You do have current loading, wave loading. You also have earthquakes. Those are ultimate limit state cases, right? You have also the hydrostatic loads, because the deeper the level in the water, you have more pressure there. So the structure needs to also take that into account. Now, and for floating, a floating device is obviously much more affected on its motion for the waves and for the currents, which changes the dynamics right away of the structure and how the load is distributed. So that's also quite an engineering challenge. You need a lot of simulation tools for this and really test it in the field. That's why a few projects are only 3, 6 turbines, because it needs to be tested. Well, that's from the engineering perspective, but also from the project perspective. Companies that go initiating this is their first time, right? So they want to have an experience of how this project goes, how it should feel financially, the contractor, the design, the manufacturing, the insurances, the interest rate that they're going to get from a loan, because the first time they are going into this, right? So it all affects the business case. Now, the key aspects about the installed capacity. We can clearly see that, okay, people hear about the United States, people hear about Europe, but if you go to the facts, it's not that they're not there, they are there actually, but the continent leading the way in the installed, I think, the cumulative installed capacity is Asia, with more than 250 gigawatts installed, followed obviously by Europe, then the United States, and below, I thought, okay, let's put a few countries in our continent, south part of the continent, South America as well, just to see where we are at, right? So you can see that this is not offshore, this is onshore and offshore. I think this is both. It's completely wind energy. You can see that after around 2015, then Asia started taking the lead. And when we discussed about the aspects of the project, that the technology is not the only, that engineering is not the only aspect of it, there are many. So you can divide this into sort of 4 stages. Now there's a lot of literature, and you can talk with other companies, and they will give you different values maybe in the planning and development and implementation. So these are rough estimates. So, but I think you can group them in 4. So first is the planning and development, right? Then the implementation, then the operation, and then the decommissioning. Now I'm going to start from right to left here. So decommissioning is at the end, right? The wind farm has lived his production life. The case is closed, and there are a few options. Either you uninstall them, either you make a renovation, like a power upgrade, or you put something else in the turbine, or you completely change the business case and you still use the foundation to put a different turbine over there, because after 25 years, you can imagine that your power rating is going to go, it's going to be bigger. The operation of a wind farm is around 25 years, right? That's also the value that we designed the wind turbines to last. So in this time, in this phase, you have the operation, normal operation of the wind farm. You have the maintenance and the service of the wind farm, because you need to also continuously monitor the scour protection. Now, the scour protection is when you have a fixed support structure, a fixed monopile, fixed jacket at the bottom of the sea, the current starts to swipe away a part of the soil around the structure, right? And that is not good for the support structure. You need that part, right? So there is the scour material that it is installed is set in place such that you can actually comply with the engineer in terms of having a fixed point there, right? Now, in planning and development, it's around 3 to 5 years. It could be a bit more. It really depends on many aspects. You need to find the good location as a company that wants to invest in it, right? And in finding a good location, you need also to make environmental studies about the soil. You need soil properties, so you know that you can install some turbines over there. You need meteorological data to actually assess what is the wind condition over there, because that's all you need. Well, not all you need, but it's part of what you need for your assessment, your business case. You need oceanographic data, because the wave and the current are going to affect your structure, right? So that defines defines a lot of the geometry, the heights where you put the door, how high it's going to be, how heavy it's going to be your structure, right? And all this data is implemented into the design. And the design, I put asterisk here because it can get in the phase of implementation. It can get, but normally in this design you have an initial design, very rough estimates. You make tenders with those, and then you have more of an iterative, detailed design. You have the layout. You have certification aspects of your design. At the same time, well, not entirely the same time, but a bit before, still in the planning and development, you need to come up with the finance. there's no company, I think, big enough that has that much money to finance a project like this. You'll later on see why. So you get loans, not you per se as a simple person, but the parties involved get loans. And then, of course, you need to involve the citizenship in case it's in the onshore, and in the offshore. Sometimes the state already assigns like, okay, these are the areas we are going to do tenders for, the areas that we want the wind turbines or wind farms to be installed. So companies compete for that. Now, the implementation, but between 2 to 4 years, what does it entail? It has the final financial closure, which is practically where the order is set. Like after all this, the company, the energy one who owns the wind farms, okay, I'm going to hire this. They have been in conversations already and previous agreements, early works agreements, etc. And the order is made. The order for the steel, for the parts, for the turbine, for the foundation, all that's made. Then also happens that you need to do some pre-construction and construction work, because you need to prepare the soil, like the scar protection, for example. You need to prepare the soil and the place where the turbines are going to be installed. And then, of course, afterward comes the installation and the connection to the grid. Installation could last, like just installation could last 1 to 2 years, right? It could, well, sorry, just installation and the connection 1 to 2 years. If you are very fast, just the installation aspect of its own, depending on the size of the wind farm. But I think I've read a few that you can do it 1 year or 6-7 months. But of course, this is an isolated aspect of the implementation phase. Now, a way to take a look at the cost of a wind farm in a very simplified manner is the levelized cost of energy, right? Because otherwise, for a business case, you have a cash flow, you have your investment, you have a lot of things that need to be bought. So the LCOE is very useful here, and also to compare with other technologies. So it's a summation of the capital expenditure, the operations, and the decommissioning. Right? It literally means what is the minimum income that the project needs to have with respect to the megawatt hour or energy produced, given the fact that taking all the costs into account along its lifetime. So it is proportional to the big investments you do, the operations, the maintenance, and the service cost, and the energy, the net energy that you are going to generate, and the interest rates, and the lifetime of the project. Now, how to break this down? This is an example for the US market. This was done by the National Renewable Energy, by the NREL in the United States. It's for 2021, so very recent. And you can divide this in four. The turbine, at least what NREL is indicating, is around 23% of the cost during your lifetime. Just that's the representation of a turbine. Then, of course, you have the development, the engineering and management, the substructure and the foundation, the electrical infrastructure, the cable installation. They all represent around 30% for the US market. And then you have the financial capex, the financial capital expenditure. You have contingencies. You need to have financial, money for contingencies. Something happens in design, something happens in installation, in construction. Cash flow needs to keep running. So you have a contingency there for the commissioning, for the construction, for bonds, probably. That has like a 15%. And then your operation expenditure, they just went up right away. Operation and maintenance. Look how big maintenance is, like 80% off. So it's about around 33%. So it's easy to break it down like this. Your balance of system, your turbine, your financial, and your OPEX. This is another example. It's for the UK, but practically, by the way, the links are here, so you can check them later on. But in this case, an important thing to highlight is the maintenance and service the wind turbine on its own and activities around a wind turbine and installation are just the biggest thing. That's the whole aspect. Now, how do you use this? Because we mentioned about that this is very good to compare with other technologies. Now, there are a few links here, one from a Bloomberg analysis in 2018, which is not up to date. It's not up to date. Later on, I'll show you a new one from Fraunhofer Institute in Germany. But let's take the data 2019. The LCOE for wind energy, it's around, I think, wait, I put the dollars, but I think this is actually euros. I made a mistake here. Anyway, but in the plot you can see for the offshore wind and the onshore wind. Yeah, sorry, the onshore wind is between 58 to 6 US dollars per megawatt hour, and the offshore is from 99 to 175. Right? If you compare that to onshore wind plus battery, biomass, nuclear, right? Pump hydro, non-tracking photovoltaics in the battery system, and other aspects, you can immediately see, like, forgetting about all the complexities of the other systems from a financial perspective, that wind is already ahead, because the cost overall during the lifetime is relatively low. At least the margin is relatively low, way much lower than the other alternative that you see there, like biomass, for example. It's not that I'm against biomass, but it's just to give an example of another renewable energy source right away, right? It's a range, right? So it does not represent, it does not speak of every wind farm project, does not speak of every biomass project, and so on. It's just an average. Now, this one, there is a practical book called Operational Guide by Joachim Tax about installation and so on, but I found it very useful for an understanding of a few costs. And I'm going to say it's an approximation, because getting the cost, I like the actual costs, not just per megawatt hour, but the actual cost of investment is a bit difficult. And you know, companies are, it's not that they are jealous of that, but it's highly classified in information. At least that aspect. For every 100 megawatt capacity, it's apparently 17 million US dollars, which is a lot of money, right? And the engineering is around $480,000 for the wind turbine. And I put here a few asterisks, because it's not just buying the wind turbine, it's about all the related activities that the wind turbine contractor is obliged to provide once he provides a turbine, right? Not just provide a turbine, that's it. It doesn't work like that. So there's assembly guidance, there's assembly operations, there's assistance in operations that the wind turbine manufacturer has to be involved during installation, during the commissioning, during the decommissioning, all those components. So for big ones, it's apparently around 14 million US dollars per 10 megawatt of a wind farm. Now this one I'm not gonna go through it because it's a lot, but I made a few years ago a table which I think should be useful for you guys about some actors that are active, some companies that are active within the wind energy industry. So I've divided by the WTG, which is the wind turbine generators, or the wind turbine contractors, and their websites. I work, for example, with Siemens Gamesa for all these years, but there we have competitors like Vestas, MHI Vestas, General Electric, which these three players are coming with wind turbines that I told you before, around 14 megawatts, 12 megawatts, the very big turbines. And you have other participants like Enercon, Nordex, Symvion used to lead a long time ago, but I think it was acquired already by SGRE. It's no longer existing, as far as I know. You have Goldwind and Shanghai Electric in China, and you have plenty more. So this is for the installed capacity, the offshore, and some comments. So I'm not going to go into detail because this is for you to read later on. Now, again, what have you guys understood what I've been commenting in the meantime? Do you have any questions so far? Do you think are we still good in time? Let me know in the communication aspect in the chat. Okay, I'll continue. So for the structures, I'm going to show you a few pictures. You have the rotor nacelle assembly, right? The tower, the transition piece, which is what connects the substructure with the turbine. And the substructure could be a jacket, a monopile, or a floater. Here you see two pictures, right? To the left and to the right. To the left one is mostly fixed options in which you have gravity base, you have suction buckets, monopiles, fire puts, jacket, etc. But the one that dominates the most by far is the implementation of the monopile, followed by the jacket. Right, by far the monopile. The monopile used to be thought that it will only be good for 30 meter, for maximum 30 meter water depth. But there are projects that are actually challenging this, right? So, yeah, there are projects who are challenging this. But we know already for the project of Provier Grand Large, PGL, that at least for that floater device, 70 meters water depth, the project is going for floaters, right? You have a jacket, so floater is practically around 50, 60, 70 meters water depth. You have tension leg platforms in which you have a floater device, and then the chains, or the let's call it ropes, but the catenary chains that you have them are tensed, right? They are tensed immediately, all the time. There might be some changes here and there, but they are tensed all the time. That's one dynamics. You have the semi-submersible one, in which the chains are not tense right away, but because the chains are there, it restricts the motion in a sense, and it allows a certain motion. And then you have this spar, in which is practically you have to put it mildly, like big monopile that can actually float. How big are these monopiles, for example? This is for a project called Gemini. Wait, something happened. Ok, perfect. ¿Desde dónde es que de cuándo no me escuchan?
Alberto, más o menos la diapositiva anterior.
Desde esta.
Sí, si quieres podemos retomar desde ahí.
Ok, listo. Vamos a retomar desde ahí. Entonces, algo pasó en el celular porque ahí sale que estoy conectado todavía, pero déjame más bien, yo me desconecto del celular para que no exista ningún percance. Dale. Entonces, lo hago así. Okay, vale. Okay, so for the structures, you have the fixed ones to the left, and you have a fixed and also the floated ones to the right. So to the left one, you have gravity base, suction buckets, monopiles, tripods, jackets, etc. But the one that by far dominates the market in the offshore is the monopile. It by far dominates it. It's one of the simplest solutions to design and to manufacture, and one of the most proven technologies. So companies, investors, they all mostly want to go with it. It used to be thought that you could only perhaps reach a maximum water depth of 30 meters, but I've been seeing that being challenged already. So by far, these numbers here does not mean that the monopile can only be implemented up to 30 meters. But certainly for deeper waters, what we saw already for the PGO case, for example, then in that one you have for 70-meter water depths, then you do have to use a floater, for example. There are three types of floaters, more or less. You have a tension leg platform, you have a semi-submersible, and a spar. The spar is most likely just to pull it very informally speaking. It's like a big monopile that can float, and you have control by the catenaries lines anchored to the seabed, right? So it does have a lot of motion. Also, the semi-submersible, in this case, the floater design is different. It's submerged a little bit, and some part is not submerged. And then the catenaries, so the chains are not tensed, but in the tension leg platform they are. These all have different dynamics, and by having different dynamics, that means the design is completely different, and the structural loads are the way you design them are different. Now, for the monopile, which is the most proven technology to work in the offshore, the most trusted one, this is an example for a Dutch project. It's called Gemini. It's a very large wind farm. It has around 150 units. To the left, you see a picture taken in the field when they are transporting one of these monopiles via remote control. Like this equipment is remotely controlled, right? The size, sorry, the weight of these monopiles is around 850 metric tons per unit, and this is just the monopile, and it had to install 150. The wind farm is around 85 kilometers from the Dutch land, and to the right you see a transition piece, which is what it's located on top of it. But this is not for that project; it's for another project. The transition piece. What is it important? Why is it important? There are some designs that are not requiring that, but most of it is grouted to the monopile, because the monopile is hammered during installation, right? So if it's hammered during installation, you can really damage the interface over there. But in the transition piece that you see to the left, you see it's been installed with the tower on top. You have a platform. You have what is called a vid crane, just a crane to assist the personnel in there. So that whole platform is implemented for the installation and for managing devices and access inside the turbine. The boat landing gear, or the boat landing not platform, but yeah, the boat landing platform, it's also attached. You don't see it very well here, but it's also attached to the TP structure, the transition piece. The floaters. Well, this one I briefly discussed already. It's in France. It's lesson 2014. This is just a picture to tell you exactly what kind of structures need to be analyzed when we are talking about about jacket structures, right? An example. This is not a picture of that project, but for a project called Beatrice, you could have 30 units. The water depth ranges from 30 to 60 meters, if I'm not mistaken, for jackets for its implementation. For this project, had a massive weight of some different aspects, some issues, and they used to need to design against this. In this case, I think this project never ran because the structure was not good enough, and also some other aspects of the business case. But when you have innovative solutions, you sometimes they do fail. They become difficult to assess in the sense that there's not standard approach to it. There are some standards aspects to it, but you always there's always a risk, and some of them need quite more research. Now, practical aspects, guys. There is actually few wind farms that have apps, mobile apps that you can download right now. They are free, and you can check the power production. You can check the power production. You can check the wind speed. You can see how this wind farm is performing, is doing. So it's information you could use for a class, information you could use for analysis, to check your knowledge, etc. One of this is, well, there are two actually, for Gemini wind farm, the one we discussed about already, 150 units, and another Dutch one called Friesland. In these two, these are just snapshots. These are just snapshots that you can see immediately the gigawatt hours of the energy being produced. You can follow that on your own. It's free. And have a short video there of Friesland wind farm, but I don't think I'm going to show it in a moment. I think I may have used too much time. Apologies for that. We're about to finish. And with these useful ads, how useful are they? Now I'm just taking an example. It's an example, and the following is only an approximation, right? It does not pertain to any specific performance of this wind farm, but it should give you a hindsight and an idea of some costs, right? Let's use the LCOE, right? So this is not the LCOE of the wind farm itself, of Gemini, but rather from a source of the Fraunhofer Institute in Germany. This is from 2021, from 2021, yeah, in which they are comparing different sources, just like the one we saw about Bloomberg in 2018. Yes? I heard someone saying something, but I cannot understand that very well.
¿Me escuchas bien?
Sí, ya te estoy escuchando, pero se escucha como entrecortado.
No sé, ¿acá me escuchas mejor? ¿Me escuchas mejor? Sonido. ¿Aló?
No te escucho mejor, pero te entiendo, te puedo entender. Dime.
Ok. Alberto, tenemos algunas preguntas de los estudiantes y el problema es que el tiempo no nos va a dar, o sea, no alcanzamos a terminar la presentación. No sé si quieres que pronto corte un momentico y vamos haciendo las preguntas, porque si no el tiempo se nos va a quedar muy corto. ¿Qué opinas tú?
Claro, por supuesto.
Listo, Alberto. Entonces, la primera pregunta, ¿quién tiene pregunta? La primera pregunta.
Hi, did you hear me?
Yeah, I can, I do.
Okay, talking a little about the layout of the turbines, what strategies from material engineering have been proposed to mitigate the damage caused by corrosion in the turbines and their infrastructure, since it is known that the sea is a highly hostile area in this matter?
Yeah, okay, good. Yes, the main protection that you get, the corrosion protection, is the coating. So especially for the foundation, either the monopile or the jacket or the floating foundation, there is always a coating. it's not a paint though, but it's a layer that is implemented on top of the foundation to prevent it from oxidizing, right? And also from a design perspective, that pretty much depends on the standards and which company is designing. A certain level of degradation needs to be taken into account for the design during the lifetime. But the main defense is the coating, for sure. The main defense is the coating. So it's not per se on the material. To be honest, not like you add something to make it water oxidation resistant, but there's a coating that it's added on all the foundations. There's also a bit of a coating, obviously, in the tower itself, but in the foundations, the requirements are stricter because obviously you are in the sea. Does that answer your question?
Yes. Yes. Somebody have some other question? No? No questions? I have other question. That coatings, that is a multi-layered coating, is taken count in the LCOE index?
Yeah, it should be. I mean, it's a small detail, but yes, because practically one of the aspects of the LCOE, right, is the foundation design, the foundation installation. So it's part of the bill of materials. It's a very small part, to be honest. It's a very, very small part. The cost should have no impact on it.
So how is the bigger part of the maintenance system of this kind of structures?
What is the what, sorry?
What is the bigger part of the maintenance of this kind of a structure?
Oh, for the foundations or for the wind turbine and so on?
Just foundations or all the structure?
Oh, so the maintenance is, well, for that one I can only reply just general because it's not exactly what I emphasized in when I was working. But the maintenance and service is not only for the foundation, but it's for the whole turbine. I think I wouldn't know how to pinpoint to which one is the most impacting activity. But for sure, if the coating is wrongly selected, and let's say for some reason it was just wrongly applied, then it's gonna have an impact because you have to go there and try to solve that corrosion code, right? And it's gonna affect your lifetime. So it will be a driver. But in order not to be a driver, it has to be very well implemented and designed. Like this is the certain level. It's not like it's a certain level that you want. There's a requirement already. There's a minimum requirement of the of how good the corrosion protection is. It's called it has a grade out called CX or C5, but that's just in the standards. It's just to say there's a level of how good this correction of this coating has to be, and you have to meet that from the very early start of design. And is also pushed by the client, by the customer. You know, you have to abide by these and these standards from Eurocode, from bodies like certifying bodies like DMV, which is a certifying body, in which they say, okay, corrosion protection for turbines is like this. Yeah, and for the LCOE, I think so it could be up to 18 or 20% of a share, at least, yeah, which is a big share part. But it's not about the coating; it's about the whole process of the maintenance and service, and that goes with the operation as well.
The wind energy production model on land or onshore, and the wind turbines installed in the sea, the producing energy, now of offshore wind energy. So as technology advances, we call develop another component for the production of it, and how efficient.
Mm-hmm. how efficient, go ahead, repeat it.
And how's efficiency,
Si quieres, habla en español, si te hace muy difícil, no hay ningún problema.
Sabiendo que pues, los dos modelos más utilizados en el planeta de la energía eólica son, para ser más concreto, los molinos y los autogeneradores en el mar, ¿sí me entiende? Entonces, avance la tecnología, como la tecnología avanzando tanto durante esos años, ¿será que de pronto en un lapso de tiempo nosotros los ingenieros podemos diseñar algún tipo de componente o de mecanismo para de pronto competir con los dos modelos ya patentados?
Para integrar aeromotriz con motriz.
Bueno, mira, no te entiendo exactamente la pregunta como tal, pero o sea, tanto en el onshore, en inland, está prácticamente la foundation, el support structure está embedded en el suelo y tú tienes la turbina directamente. Ya cuando vas al offshore, en el costa afuera, ahí es cuando hay varios tipos, pues la mayoría es el monopile. Ahora, claro, como ingeniero o trabajando en una firma, si quieres trabajar en un diseño innovativo, claro, lo puedes hacer, eso no hay ningún problema idóneamente. El problema que hay es que, pues, de manera práctica, el monopile es el que por ahora viene siendo considerado uno de los mejores, porque hay un buen track en la producción, en el sentido en que ya la industria ha cometido varios errores que ha tenido que cometer, ha aprendido de ellos, se han implementado, hay mejoras en su proceso de manufactura, ya se entiende más cómo es el servicio y el mantenimiento de estas estructuras. Entonces, todos esos aprendizajes ya están incorporados en la industria, por así decirlo, ¿ya? Entonces, venir a competir con eso, pues tendrías que ver entonces, uno, ¿para qué quieres competir con una tecnología que ya está funcionando en ciertas zonas? ¿Por qué no mejor desarrollar o trabajar en un mercado donde, por ejemplo, el floating el floating wind turbine para unas profundidades mayores, como por ejemplo son 70, 60 metros de profundidad o 70 metros de profundidad, donde se sabe que por ahora pues, el monopal no cabe, ahí eso no se va a meter en ningún proyecto con esa subestructura. Ya. El monopal como tal, a ponerlo en términos demasiado sencillos, es lo que es un cilindro. O sea, de forma estructural es un cilindro. Hay cosas adentro y hay muchas más cosas que decir, pero de la forma como de primary steel structure es un cilindro. Entonces, es la otra forma de que se ha tratado de competir es con los jackets. Pero ya para cerca del shore, de la costa, pues, monopal por lo general está dominando. Claro que esto depende del terreno donde se esté, cómo son las condiciones para elegir entre jacket y monopal, pero por lo general, si la profundidad no es tanta, no diría monopal. Una diferencia importante es las cargas inducidas por el oleaje, lo que se le dice como el wave loading. ¿Por qué? Porque en el wave loading o las cargas inducidas por el oleaje, tú tienes el monopile que tiene un área transversal que es un círculo, ¿sí? Okay. Entonces, prácticamente está recibiendo todo el impacto de las olas y todo el impacto de las corrientes, ¿ya? Y cuando tú tienes una chaqueta, jacket structure, es lo que se le llama lattice structures, entonces tienes eso, todos los beams, todos los trusses. No es que sea invisible al oleaje, pero es casi. Entonces, claro, tus cargas con respecto al oleaje van a disminuir.
Ok, para que me quede claro, entonces, lo que usted me está tratando de decir es que en vez de coger estas patentes que están ahora y transformarla en un mecanismo que nos pueda como, o sea, para hablar en palabras coloquiales, inventar algo nuevo, usted lo que me está queriendo decir es que perfeccionemos esa...
Te voy a corregir ahí. Es que no hay, bueno, obviamente en la industria hay patentes para un montón de cosas, pero si tú vas a trabajar para una empresa que hace monopal, no hay patente en monopal, la patente del monopal, no, eso no existe. Lo que sí hay es, por ejemplo, que era, te voy a dar un ejemplo en la torre, en el monopal, un cierto tipo de marco para la puerta, ya, porque eso es importante porque hace unos concentradores de esfuerzo y tal. Entonces, la forma como se manufactura y cómo se implementa, la compañía Vestas tenía una patente que estaba jodiendo a toda la industria. Entonces, no podías, por ejemplo, no podías utilizar toda una placa entera y ahí mismito hacer ese doorframe, esa entrada. No se podía, ya. Entonces, así es como se han creado las patentes. Pero por ejemplo, no es que exista que uno diga, ok, Vanor o alguna otra compañía, no, Vanor no, perdón, Vanor es la instalación. Digamos una compañía que hace el diseño de las fundaciones va a decir, ok, como yo voy a hacer un monopal, tengo que pagar esta patente. No, eso no es así. Ya, no hay patente con respecto a ese sentido. O sea, si me doy a entender, ¿es eso a donde ibas?
O sea, cuando yo le hablo de patente, en mi concepto es como decir, los dos mecanismos que ahorita se instalan para generar energía eólica, que ya sabemos que es el onshore y el offshore, a mi pregunta lo que va es, usted lo que desea o lo que quiere es que nosotros no, o sea, perfeccionar esos componentes, esos mecanismos que ya existen, o de pronto usted cree que más adelante, a medida de la tecnología avanzando, nosotros podemos innovar un nuevo mecanismo o un nuevo componente para generar esta misma energía.
Tú dices algo diferente a una turbina eólica.
Más o menos.
Ok, ya eso es otro tipo de pregunta. Eso es otro tipo de pregunta. No sé, de lo más seguro, no tengo idea, no sé, pero vale, si tienes ideas, pues zámpate a ellas. Claro, mira, en otros campos también existen para sacar energía en el offshore que no son directamente, o en el mar, que no son directamente relacionados a la energía del viento, que son, por ejemplo, hay ciertos dispositivos que utilizan el movimiento del oleaje, sub y baja, para producir electricidad en base a este movimiento. ¿Ya? Es totalmente diferente a un parque eólico y creo que he visto unos cuantos conceptos que son nuevos. Pues tiene su potencial y que compita como tal, es que esa no es la mejor forma de ver esto. Esa sencillamente es la mejor forma de ver esto, y te lo digo porque el enfoque que yo le doy, pues, es que tenemos una crisis climática. Fin, se acabó. Tenemos una crisis climática. Obviamente estamos en un sistema capital, obviamente el capitalismo y tal. O sea, el negocio tiene que ser sustentable de alguna forma, pero entonces toda solución extra que ayude a la generación de energía que no sea de energía renovable, que no sea en base a gas, petróleo, carbón, para la humanidad es bienvenida. Claro que tienes que hacer tu buen marco negocio. Ya. Pero, ¿qué te recomendaría? Como ingeniero, hombre, si te gusta la parte, si estás interesado en la parte de energía eólica, empieza a investigar. Empieza a investigar qué compañías, empieza a investigar qué conocimientos debes tú demostrarle a ellos o que vas a aprender para poder trabajar en este entorno. Porque de sí como tal, no, que voy a competir, quiero competir, pero no sabes en qué te estás metiendo. Primero analiza dónde te estás metiendo, primero analiza qué oportunidades hay, aprende las habilidades y comienza a trabajar ahí. Ya. no tiene que ser necesariamente por ingeniería. Si te gusta ir por la parte de inversionista o la parte económica, pues ya debes ver cómo encuentras tu camino.
Listo, Alberto. Dos preguntitas y más corticas, por favor, respondamos lo más cortico. Qué pena, Alberto, acosarte, pero es que estamos ya corticos de tiempo. Entonces, la primera pregunta.
Hello, Albert. The first question is, what is the difference about the life of the useful, about the offshore system and the old system in the 25 years, what you talk about in the presentation?
So you mean the lifetime of the lifetime for offshore wind turbines for its design is around 25 years. I'm not entirely sure how much is for onshore turbines, but the thing is that the investment that you are going to take, the LCOE, if you look at it from that perspective, the LCOE is higher for the offshore than for the onshore. Onshore has a higher track because it's what was first implemented, right, rather than offshore. So the installation, the investment cost is higher for the offshore. And well, if you're selling electricity, you also need a longer return period, right? You cannot have it too long because otherwise there's no business case, right? When you make your business case with flow chart, etc. Well, not you, but the investor. So I think that would be like that has an impact. When will they be close to each other? I don't know, but the offshore is closing the gap soon. So obviously it's not going to be next year, next 2 years, and next 3. But probably less than a decade, maybe less than a decade, some areas offshore can be as good as onshore from a financial perspective. I'm not sure. Divagating in this is quite in the air, but taking into account the investment in the offshore is higher.
No, con respecto a la inversión, claramente el offshore es más costoso, pero con respecto al tiempo de vida, no sé si no entendí o no me quedó claro. ¿Sí te quedó claro? Sí. Bueno, listo. Siguiente. Aquí tiene una pregunta con respecto al desmantelamiento de este tipo de estructuras.
Buenos días. Mi pregunta va y dice, ¿cuál es el proceso de desmantelamiento y eliminación de las estructuras eólicas offshore al final de su vida útil?
Uy, me corchaste. Ahí sí me corchaste. O sea, hay varias opciones. Son las generales. Hay una de esas que se puede utilizar, es que una vez que se llega al tiempo final, al final del periodo de la vida del parque eólico, muchas compañías como Siemens, por ejemplo, estaba ofreciendo, ok, te damos un upgrade kit. Es decir, mira, hay un cambio en el controlador y hay un cambio, hay como unos cambios que se le ponen a las aspas para que se incremente, ¿cómo se dice? Se incremente la producción, se disminuyan las cargas y tal. Pero claro, eso no se hace a la ligera porque para eso primero se analiza si, ok, durante esos 25 años, ponle tú, 20 años que duró el parque eólico, si todavía tiene, entre comillas, tiene vida. Ya. Entonces, para eso tuvo que haber una campaña durante toda la vida, un seguimiento de las cargas y eso. Y el contratista, bueno, se le pregunta al contratista, se da toda la información y ellos pueden decir, ok, vamos a ver si a este se le puede extender la vida. Ese es un caso. Ya, ese es un caso en el cual utilizaría las mismas turbinas ahí y se hace un contrato nuevo otra vez de mantenimiento, de servicio y de garantía de lo que se está ofreciendo. La otra opción, que es la desinstalación, sinceramente no sé qué pasa después de que esas turbinas son desinstaladas. Ahí sí, ese tema yo no lo manejo. El otro caso es que pero después, es que se desinstalen y de pronto, ya sea que la fundación o la subestructura aún pueda ser útil y se ponga una tubería encima, o que bueno, se tiene que desinstalar todo y poner un parque eólico ahí otra vez, pero esta vez más grande. Más grande no, con mayor capacidad. Ya todo depende del cliente, la verdad. Y es un span de 25 años, entonces la verdad no te sabría decir. O sea, te puedo decir esos tres generales. Esas son las tres opciones que hay.
Yo creo que si se sobrediseña un poquito la estructura para que las cargas de fatiga, de pronto, para disminuir el impacto de las cargas de fatiga, se puede reutilizar la fundación, como vos dices, y lo que sí toca sí o sí desechar al final de la vida útil son las aspas, porque las aspas casi siempre están hechas de materiales compuestos, ¿sí?
Sí.
Entonces, y estas no se pueden reciclar, y estas no se les puede extender la vida útil de la fatiga, del desgaste que han sufrido por la fatiga. Máximo.
Sí, tienes razón en un sentido, con respecto al rotor, la diferencia entre el rotor y la estructura metálica. Pero ahí hay algo que, bueno, el sobrediseño, como ahora como hay competencia, claro, entonces el sobrediseño no se implementa de manera activa, porque entre más sobrediseñes de manera voluntaria, más costoso te va a salir la turbina que estás ofreciendo al cliente. Ya estás en competencia con los demás. O sea, ahí viene la parte del capitalismo, que es la parte financiera. Entonces, ¿qué se acostumbra? Se trata de ahorrar lo máximo posible. Ahora, el diseño que va a hacer las cargas es una proyección. Esas cargas no es como, por ejemplo, en una planta térmica que tú sabes exactamente cuál es el flujo de producción que vas a tener. No es así. Ya, son estimaciones, te basas en estadística, entonces las cargas que el parque eólico va a experimentar en su vida no son necesariamente las mismas con las que se diseña. Si está bien diseñado, deben ser menores. Obviamente deberían ser menores. Ahora, ¿qué tanta extra de vida útil te queda? Ya hay que analizarlo en el caso. Pero el sobrediseño voluntariamente te puede llevar a que no compitas. O sea, no a ti como tal, a mí como persona, pero a que el contratista que está vendiendo la turbina eólica esté en mala posición para vender porque sale muy costoso.
Listo, Alberto. Yo creo que con esto ya cerramos porque tengo una conferencia ahorita a las 11. Tenemos una preguntita puntual del profesor Rafael Turán.
Sí, Alberto, gracias por la presentación. Si es la última pregunta, yo creo que puede ser, pues dada tu experiencia, ¿cuál sería o cuál crees tú que es el aporte que podemos hacer como universidad? O sea, en materia de investigación.
Papi, no joda, ¿cuál es? Perdón, eso fue muy informal, pero bastante. Mira, yo lo quería comentar y...
Trascendentales, porque, o sea, no que quede una investigación metida en una biblioteca y ya, sino algo que en realidad contribuye.
No, trascendental.
Pero ahí también hay que aterrizar al hecho de que vos sabes que aquí en Colombia las estructuras eólicas apenas están empezando a implementarse aproximadamente, no llevamos ni más de 10 años implementando sistemas eólicos.
Sí,
y comercialmente apenas Veolia y Ecopetrol y EPM están haciendo inversiones. Pero la pregunta es cómo podemos de pronto saltar de la ciencia a esta industria. No hablo yo, por ejemplo, solamente de Colombia. Podríamos tener una proyección hacia Panamá, hacia de pronto las islas, a las Antillas, hacia, no sé, ¿vos qué opinas?
Bueno, mira, sería muy bonito decir que desde la parte ingenieril nada más, pero eso no sería realista. Ya, entonces, como tal, el país que ya comenzó a hacerlo con la ruta de progreso, se necesitan crear políticas de inversión y para atraer la inversión, pero también no es solamente atraer al inversionista, es que, por ejemplo, a países como Francia pusieron una restricción que, bueno, si usted va a instalar acá, bueno, el grupo de inversionistas va a instalar acá, bueno, parte de la mano de obra que sea acá, tienes que al menos instalar un punto de fábrica, algo así. Entonces, no sé qué tanto pueda contribuir, claro, la universidad con respecto a la decisión política, pero sin embargo, sacando la parte de ingeniería, el departamento de economía y de la parte de leyes, de política de la universidad, puede investigar, cuáles serían las buenas políticas para recomendar al gobierno para que este conocimiento se quede. Ya, porque si parte del conocimiento se queda, entonces se fortalece o se empieza a crear lo que es la mano de obra. Ya, la mano de obra, el ingeniero que puede participar, ya trabajando remoto o trabajando por ejemplo, para el mantenimiento. Ya, lo que es el mantenimiento del servicio, por ejemplo, es algo que se puede entrenar y se podría hacer con personal local. Ya, entonces, esa es una parte. Hice por la parte cómo es el mantenimiento y el servicio de estas turbinas eólicas. Ahora, con respecto a aprovechar, por ejemplo, la capacidad que se tiene, da como la parte de ingeniería, sí, porque primero tienen que haber políticas, en mi opinión, para llamar la inversión. Y si, por ejemplo, una compañía, digamos, ya está incentivada por el gobierno en abrir una oficina acá, ese es un salto bien grande, pero si digamos ya está incentivada, tiene que encontrar gente capacitada. Entonces, la universidad puede capacitar a la gente en ese sentido. Ahora, ¿cómo se puede capacitar con herramientas que se utilizan en la industria? No solamente la parte teórica. Mira, para empaparte del tema, uno de los cuerpos de certificación que se llama DNV, en la presentación que yo tuve ahí, que por cierto, mis disculpas que me demoré demasiado, me sobreentusiasmé, hay un enlace en el cual tú puedes acceder a la página de ellos y para el sector académico, ya si se hace el papeleo correcto, DNV te da acceso gratuito a todos los estándares que ellos tienen. Entonces, de ahí, por ejemplo, ya se podría formar un grupo que vamos a analizar cuáles son los estándares, de pronto hablar con el cuerpo de certificación DNV y decir, hey, nosotros queremos meternos de lleno con respecto a la energía eólica. Ya. Y entonces empecé a analizar cuáles son los estándares, cuáles son los requerimientos para la instalación, para el diseño, para los estudios meteorológicos, para las etapas del proyecto, ¿ya? Eso es una parte, es muy general, es una parte, pero no, adición, Taiwán, ellos han hecho algo no parecido, pero muy relacionado a esto, y es lo siguiente, pues yo trabajé con ellos para el proyecto de Yunlin. ¿Qué ha hecho Taiwán? Ellos pidieron, listo, usted va a instalar acá, lo certifique internacionalmente, pero el sello de aprobado de que esto se va a instalar lo tiene que dar un cuerpo taiwanés. Ya. ¿Qué significa esto? Que por ejemplo, Siemens Gamesa y el cliente van con DNV, pero ya no es solamente con DNV, entonces ahora tienen que explicarle y tienen que hacer todo el proceso de certificación también con una compañía local. Ahora, ¿qué hizo el gobierno de Taiwán con respecto para fomentar esta creación de empresas? Porque fue creación de empresas. Vale, ellos son responsables. Ellos tienen un título de PE, Professional Engineer. Ellos firman y son responsables. Es decir, que si este proyecto falla en estructura, alguna catástrofe, lo que sea, el gobierno no va primero ¿cómo se dice? Al inversionista extranjero. El gobierno va primero a la empresa que hizo el sello de esta certificación de Taiwán. Entonces, esa es la parte de conocimiento que yo veo que Taiwán está atacando. No sé por qué. Porque estos cuerpos de certificación que son nuevos, son nuevos en el mercado, tienen que empaparse, las empresas tienen que compartir información vital que no quieren compartir, como por ejemplo el brief de cómo se diseñan ciertas partes. La empresa no quiere compartir eso. Eso es conocimiento que prácticamente te da ventaja, pero ahora tienes que compartirlo con un cuerpo extranjero, el cual no había entablado una relación. Entonces, así se puede ir formando empresas que surjan para esta necesidad y que los ingenieros se vayan, ¿cómo se dice? Se vayan formando. Obviamente tiene que haber políticas para que ayude a esta inversión, a la fomentación de estas empresas y que estos ingenieros se formen también.
Listo.
Digo yo.
Con eso ya terminamos, porque es que ya viene la otra ponencia y ya estamos corticos de tiempo. Entonces te agradezco muchísimo tu participación, te agradezco el esfuerzo que hiciste de estar acá, de preparar la presentación, de responder nuestras preguntas. Le agradezco a los estudiantes que participaron, no olviden registrar su asistencia. Muchísimas gracias por participar y no olviden que estamos en el International Week Holanda este año. ¿Cómo? En la plataforma de YouTube UPB Colombia van a poder encontrar el video, en cualquier momento van a poder devolverse a aspectos que no hayan entendido o semejante. Listo. Agradecemos a todos su participación y les deseo un muy buen día. Hasta luego, Alberto.
Hasta luego, muchas gracias.